Hello everyone, welcome back. In this video, I will be using Prosper to model a gas well and understand how IPR and VLP curves are generated and interpreted. By the end of this video, you should be able to confidently perform a basic gas well analysis. Now let's get right on into it. The first thing we do, we launch our options summary. And of course, we are working on a gas well. So the flue type we're going to be selecting is dry and wet gas. Every other setting still remains the same. So that takes us to done. And then we move on to the PVT data block. Now in this block, we are going to be entering our data as given in the class exercise that is on the screen. Our gas gravity is given as 0.65. Our separator pressure is given as 250 psig. Our condensate to gas ratio is given as 5 stb by mm scuff. Our condensate gravity is given as 50 API. Our water to gas ratio is given as 0. Then our water salinity is given as 10,000 parts per million. 10,000 parts per million. Yeah. Now for the impurities, we assume it's negligible. So now we're going to use for our gas viscosity correlation, we are going with Lee et al. Simply because it's commonly used for sweet natural gas due to its simplicity and reliable accuracy. Another option here is Carr et al. But we prefer Lee et al. Because Carr et al. Is preferred for sour gas and gas with significant impurity. So since we are assuming that we have insignificant impurity in our sample, we are going to be looking at, we're going to be choosing Lee et al. As our correlation for our gas viscosity. Now, when we are done here, we click on done. Yeah, and then we move on to the IPR section. Now, under the IPR section, that's the inflow performance relation, we are going to enter our reservoir data. Now, for our reservoir model, we are selecting the petroleum experts. Yeah. And then we enter skin by hand and we enter our reservoir pressure. Our reservoir pressure is given as 2500 psig. Our reservoir temperature is given as 180 Fahrenheit. Our water gas ratio is given as 0. Condensate gas ratio is given as 5. Yeah, we already have that. So, and after this, we also impute more data. That's for our reservoir permeability, we go with 25 as given in our exercise. And then for our reservoir thickness, we're given here that the reservoir thickness is 80 feet. And our drainage area is given as 240 acres. Our diet shape factor, which is dimensionless, I explained what it is in my previous video. So if you need to know what it is, you just go back to the last video, or my first video rather, and then you would it's clearly explained there. Now wellbore radius is given as 0.354. Perforation interval is given as 60 feet. Sorry, 60 feet. Then our time since production started is given as 0.1. Yeah, 0.1. Our reservoir porosity is given as 0.2. Yeah, so we have all our data imputed correctly. Now for this non-Darcy flow factor, we choose calculated. Um, After calculation, the value for the non-Darcy flow factor, that's D, is going to impute itself here. So after this, we click on Meg Geoscience. Our Meg Geoscience is mechanical skin, which is 5. Yeah. So when we are done with this, we validate to ensure that our formula is consistent. Okay. So now we move on to calculate. Let's see our IPR curve. So here we have our IPR curve with a skin of 5. We have an AOF, which is absolute open flow, where we have our pressure at 0. We have the highest possible rate. In this scenario, we have the wellbore pressure to be given as 0. So here we have the highest possible flow, that's a 52.8318 um, millions curve per day. So with our having done that, we click on finish. Done. Yeah. So you can see that we have our IPR curve represented in the IPR data plot. Now let's move on to our equipment data. Our equipment data affords us the opportunity to enter values, parameters for our downhole equipment, temperature, and all of that. So we're going to start with our deviation survey. Now, deviation survey tells how horizontal or how vertical, how inclined our well actually is. But from our question, we're already told that this is a vertical well. So let me scroll up. Yeah, so the well is a vertical well. So the angle of inclination is negligible. So we can just enter from the surface, we have 0 depth, and then the true vertical is still 0 since it's a vertical well, and the well is a vertical well, and top perforation is at 5,000 feet. So that means our measured depth is going to be at 5,000 feet. That's the total depth, and then the true vertical depth, since is a vertical well, is still going to be 5,000. And then we click on done. Yeah, now we move on to the downhole equipment. We're skipping the surface equipment because we are not modeling our Christmas tree and all that. We are concerned now with our downhole equipment and what is happening in the subsurface. So now on our downhole equipment, we have our parameter here. The data has been provided. For our X mastery, of course, is 0. And then the tubing, next is our tubing. And our tubing's measured depth is 4,800 with an internal diameter of 2.441 and a roughness of 0.0018. We also have our casing. Our casing depth is given as 5,000 feet, and the casing inside diameter, notice is inside diameter is given as 6.1 inches. Our roughness is also 0.0018. Our multiplier for both of them is 1. So that sums up our downhole equipment, and then we click on done. Next is our geothermal gradient. Now for our geothermal gradient, we already know that we're starting with a depth of 0, that's at the surface, and we're told from this sentence here, the well is a vertical well and top perforation is 5,000 feet, temperature at well head is 60 degrees. So we're told that the temperature at the surface, that's the well head, is 60 degree Fahrenheit. Whereas at the top perforation, that's, remember, the top of our perforation is at 5,000 feet. The temperature, the corresponding temperature there is given as 180 degree Fahrenheit. And since we're modeling a gas well, the overall heat transfer coefficient is usually between 1 to 3. So we're just going to pick an average of 2, and then we click on done because we're through with this section. And after that, let's see the summary of what we have. Draw down hole. Yeah, this is a picture. The first part of it there is a Christmas tree, followed by the tubing, and then the casing. So that looks good. Yeah. So we are done with setting up our equipment data. You'll notice the deviation survey, downhole equipment, geothermal, and average heat capacity is ticked because we have filled in the required information. So now we move on to the analysis summary section. In this section, we're going to look at the relationship between the IPR and the VLP curve. So we are going to make use of our system tree variables. So you double click on it, and you impute your top node pressure, and our top node pressure is giving us, let's see, what's our top node pressure? Our top node pressure, which is also our separator pressure, is giving us 250 psi. That's 250 psig. The water gas ratio is giving us 0, and then the condensate to gas ratio is giving us 5. Yeah. So we continue. For now, I'm not carrying out any sensitization, so I'll click on continue and then calculate. Yeah, so let's plot so we'll get a good picture of what we are to expect. Yeah, so here we see the VLP plots, which is the red line, and then we see the IPR curve, and then we see the point of intersection, which is also called the operating point. Now, we really need to understand what this plot, you know, stands for. Now, the operating point is where, that's this point, the point of intersection, is where the IPR curve intersects the VLP curve. Yes, this IPR curve intersects the VLP curve. This point represents the actual condition at which the well will produce. At this point, the reservoir can deliver exactly the same flow rate that the wellbore can lift to the surface. So simply put, IPR tells us what the reservoir can give, whereas the VLP is what actually the well can carry. Yeah, the VLP tells what the well can carry. So intersection, that's the meeting point, tells where both agree. Now, as you can see, we have a point here where we have an optimum flow, and what this tells us, the VLP has to do with the tubing size. Yes, the tubing size plays a major role in our VLP curve, whereas the reservoir pressure plays a major role in our IPR curve. Of course, other things are factors, are contributing factors, but these two, the reservoir pressure for the IPR and the tubing size for the VLP, really plays a very, very important role, because a larger tubing reduces friction losses. So the VLP curve shifts downward. This allows the well to produce at a higher flow rate, moving the operating point to the right. Now, if the tubing size is reduced, a smaller tubing increases friction losses. So the VLP curve shifts upward. This restricts flow and reduces the production rate. So in summary, tubing size directly controls how easily fluids can flow to the surface. Now that's for your VLP curve. Tweaking the size of our tube is definitely going to affect our flow, whether we're going to have more flow or less flow. Now let's see what happens if reservoir pressure declines. Now, when reservoir pressure declines, the IPR curve moves downward because the reservoir has less energy to push gas into the well. In summary, the operating point is controlled by both the reservoir energy and the wellbore performance. Yeah, so you have that. So now let's get our points. What is actually our flow rate here? Let's see, let's go to options and then so that we can get the actual flow rate and the corresponding pressure. Now let's see. So here we have about 19.778, 19.82 millions curve per day with a corresponding pressure of um, corresponding pressure of 2084.50, within that range. So after analyzing what we have, we click on finish. Yeah, we're done with all this. Yeah, so we have drawn our VLP and IPR curve, and we have seen the point of intersection. Now when you look down on this our exercise, you realize that we're giving spatial test data. So that means there's going to be a comparison between the test and actual test data and our calculated test data. Let's see how far apart, how close it is. So now we're going to be doing that on our VLP IPR matching. So now let's enter the test data. Now this test data is actually the value gotten from a real well performed on this date 18/8/2009. Our test point comment is main flow test. Our tubing head pressure is given as a 153. Our tubing head temperature, sorry, oh, there's a mistake. Our tubing head temperature is given as 153, 153, whereas the tubing head pressure is given as 1000 psig. Our water gas ratio is given as 5. Condensate gas ratio is given as 5 as well. Our gas rate, that's a 15 million curve, 15. And then our gauge depth, is given as 4500 feet. Our gauge pressure, 1920. Then of course the reservoir pressure is 2300. So we have imputed all our data. Now let's start with let's estimate the U value for this tests. So we have 2.899, which is okay. So we are setting this. It's within our range for gas wells. So yes, we're taking that. Okay. Now let's move on to correlation comparison. Let's choose the best correlation that suits this particular well. So let's select the models that is related to our gas well. Let's pick this and then this. Yeah, let's go with this, and then we calculate. So we plot. So here we're going to zoom out. Now this small blue rectangular box is our test point. So we are out to get the model that is closest to this our test point, that best represents our test point. And from what we can see is Okizioski. I hope I'm pronouncing it well. Well, I may just be using Okiz for the purpose of this video. So Okiz seems to represent our model quite well. So we go with Okiz. Finish, done, and then now we're going to select just Okiz. Now we calculate again. Okay, let's plot. Let's see what we have. Okay, now there's perfect, it rhymes perfectly. So this model is what we're going to be using for our well. Yeah, so we click on finish, done, and then done as well. Now let's compare the two and let's see what we're going to have. We're going to be using this for that. Yes, you calculate. Yes, we have a value. And then let's plot. Yeah, as we can see, we've gotten our VLP and IPR matching. For the measured, we have 15 million scopes per day. For the calculated, we have 14.684. Now, the difference between these two, between the measured and the calculated, is very, very little, just a percentage difference of minus 2.11, which is allowed. I think the minimum allowable difference is plus or minus 5, so we are within. But if you still want it to be closer to 15, which is measured, you can achieve that by tweaking your tubing size, also your reservoir pressure, and also the skin. I'm going to be showing that on my next video, so stay tuned. Thank you so much. With this, we are going to be drawing the curtains here. And just to let you know, this point of intersection is where we have our flow. Yeah, so that brings us to the end of this gas well analysis using Prosper. I hope this helped you understand IPR VLP behavior in gas wells. Don't forget to like and subscribe for more engineering content. Thanks for watching, and I'll see you in the next video. Bye.